Oh, how about that? All right. Anybody else have any other questions about anything? Yes, what you got, Vanna? More people are coming. Yay! What you got, Vanna? Oh, you're typing? I'm sorry. Oh, wait. Oh, I suck. All right, I'll have to check that. I think I remember this. All right, I'll have to look it up here. Oh, I suck. I don't know. Oh, God, I get so many freaking emails. Sorry, Vanna. Remind me at the end of class so I can take a look real quick. Okay, you might want to do that. Anybody else? Anything? Anything? Any questions from homework? All right, well, let's see if this spurs some questions. Wednesday, we're going to have a quiz on chapter 12. All right, so everybody's got that. So Wednesday, there's going to be a quiz on chapter 12. I want to show you something kind of nifty. Oh, let me see. Let me do this. If you log into Canvas, I just did this morning. I finally discovered some more things about Canvas. Can you guys see Canvas right now up here? Anybody? Rudy, are you trying to say something?
Yeah.
You can see. Okay, thank you. If you go into Canvas right now, this should be your first page. So if you click here, you'll see I just updated the overall average. It's going to show up over there. It says 0 points here because I make it out of 0 because it's not really getting put into your grade. So you have to look over here. You can see your overall average, not counting homework at the moment. So I updated that. So it's as of today. The main page when you come in is going to be these what's called modules. So here's all the stuff for chapter 12. And then here's the stuff for, we're going back to do chapter 11 today. So here's the 2 things I put up there about chapter 11. All right, you guys with me? So it's about time I learn how to organize this better. Okay, so that's all up there for you. So we're getting into chapter 11, but I want to make sure, does anybody have any questions left over from chapter 12, the correlation stuff? Antenna, is that a new, let me see. What you got? I don't know if you're typing. So I think I have one question coming. Oh, Jeebus. There we go. All right. Antenna, are you typing? I wonder. Is it? No, I'm sorry. I thought your yes was for right now for any questions. So nobody's got any questions. Okay. So in that case, we're just going to start to get into chapter 11. I will do this. So again, let me put this up here again for those of you who just got in here. If you log into Canvas, you'll see this now as your main page. So this is just, and you can still access all the old stuff. Go to assignments page. You can still access all the old stuff. This will be the first thing you see. And so down here, chapter 11 is these things. Let me go ahead. Well, let me see. I've already got these open. But if you click on those, you'll see the handouts I'm going to go over today. But I do want to point out, you can't see there's a quiz 9 yet. So this Wednesday, quiz 9 chapter 12. So let me pull this up here. Let me stop sharing. Oh my goodness. I remember being so over it when some old person was trying to use technology, and now I am that old person. Let me see. Here we go. So this is one of the handouts that you should be seeing now. One of the handouts. Let me see. Okay. Do you see the stuff about Michigan, Minnesota, Massachusetts? Right? No, Jeff. Yes. Okay. So this is on the back side of this thing called Goodness of Fit. This is chapter 11 stuff. Look how freaky that looks. We'll come back to it. I think what I'll do, a while back I said I would do this, and I think I'll do this with this. This thing is called Side 1. If we were still on campus, I would have passed this out and had you guys do this example for yourselves. I'll go ahead. I need to actually do this. Make a video showing this thing worked out, answering the questions, right? I just have to remember to do that. Slide 1 video, right? So I'll try to show you the steps in the calculator, all that kind of stuff. So you've already got the videos from lectures when we were doing it. I'll make another one for this thing, right? So if you want to try this out, you can. This kind of makes sense. This correlation exists, that the percentage in a state that have at least a bachelor's degree is somehow related to the median income of that state, right? Doesn't that kind of make sense? So you should find a correlation. And see down here, see right here where I tell you what the R has to be, like I promised? R has to be bigger than 0.482 in order to show correlation. You will get something a decent amount bigger than that. Okay. So let me come back to normal here. And let me turn off Toby. Toby, go away. Toby, go, okay. Oh, scheisse. I still have stuff up there from last class. All right, so. Today, we have to go back to chapter 11, and we have to get that new table I was warning you about. So that's one of the posts, one of the new things on Canvas. Ooh, look at that. Wow. Okay, sorry. Not enough paper towel, Jeff? Oh. So it's a brand new distribution, and I want to kind of talk a little bit about why it makes sense that we should expect this to require a brand new distribution. All right. All right. Man. So. What I want to talk about is it's going to be kind of weird. Let me say, I'm going to talk about something that we're going to end up not doing much with, but it explains this distribution. So we're not going to use Z or T in chapter 11. We're going to make up a new one. And the reason we have to is one of the fundamental things that this distribution works with are standard deviations. So, all right, this is when I wish to God I could see your faces to gauge how you are feeling about what we're talking about. But tell me, anybody, please, if I have a normal distribution, right, what tells me these are both normal distributions? Why do they look different? What is the fundamental thing that governs kind of how fat or skinny this thing is? You guys know this. What tells me how fat or skinny a distribution is? So what governs the shape of this thing? Come on, you guys know what I'm talking about. Come on. What tells me, if I say the word, you'll know how fat or skinny. So what is this? How fat or skinny, what governs that for data? What's another name for this? How something the data is. Okay, so what is it? The spread. So the spread of the data, what governs that? What tells me that? What measures that? You know what it is. What measures the spread of the data? Oh, standard deviation, yes. Okay, this is shit we know. We know this shit. This was nothing new. So why am I talking about it? Because standard deviation itself tells you the shape of plotting sample means, for example, or sample proportions, right? If you plot all of those, the standard deviation tells you the shape of the normal curve, right, guys? Is that cool? Is that all right? So the normal distribution uses the standard deviation, or the standard deviation measures the spread of the normal curve. All right. So in chapter 7 and 8, we would take samples, we would plot those samples, and then we would figure out the new standard deviation, right? I mean, that's part of what we did. So this is if I take a bunch of sample means and I plot them. Okay, and that's nothing new. We've done that before. If I take all the possible sample means and plot them all, it's going to have this spread, right? So what if I do this? So when I, all right, this is going to be an interesting day. What if when I take a sample, instead of taking the sample mean and then going and taking another sample and doing that until I get all the samples, instead of taking the sample mean of each sample, what if I take the sample standard deviation of each sample? What would that look like if I plotted all of those? Why should I not expect it to have the same shape? Because the standard deviation used to be a single thing that determined the shape. I really want you guys to get this. There used to be one standard deviation. If it was a bunch of means, I knew exactly what the standard deviation was for all those means. So I knew kind of the shape of it. What if instead of plotting the means, I plot every single S? So I take a bunch of samples, I figure out the standard deviation of the samples, and I start plotting those. Plotting, yes, I don't know why I said it like that. I don't know. Who is completely not with me right now? Anybody? It's all right. You could be brave. You can message me privately even and say, I don't know what the shit is going on right now, Jeff. Okay. All right. Either you're all not there, or everybody is okay, or everybody is lying. Okay. Some combination of those.
Professor, can you explain it again, please?
Sure. So when I create this picture, when I create that picture, how do I create it? I take every sample and plot every sample mean. Are we cool with that? That is from chapter 7, right? Chapter 7, if we want to talk about the sample mean and what the z-score is for it, I have to know the standard deviation of all the sample means. This is chapter 7. Is anybody not cool with that? You almost don't want to admit that, because then that's like 5 chapters ago. So you should be okay with that. So what I'm saying is, if I took each sample and instead of plotting the sample mean, I plotted the standard deviation, right? So instead of saying, how old are you? I'm 0. How old are you? I'm 78. And then I've got this shape. Instead of, and that's for individuals, or if I take groups and I plot their averages, right? So if instead of plotting the averages, what if I plotted the standard deviations? That is not necessarily going to have the same shape, because what governs the shape? before was the standard deviation. There was one standard deviation. So if I take a sample, I can find X bar and S, right? Right? Yes, okay. Right, as long as the sample is quantitative in nature. Right, so if I take a sample, I can find the average something and the standard deviation of those somethings. Is everybody with me? Chapter 7 and 8 and 9, I think it's, yes, okay, dealt with what if I did every single one of those and plotted them, right? As long as n is greater than 30, I get a nice normal curve. Is everybody with me? If I took every sample of size, something bigger than 30, and I plotted every single sample mean, they would have this shape. And what would tell me how spread out that shape was is this guy, right? That would be the standard deviation of this shape. That has to make sense because that's what we've been doing for a while. Okay. What if instead of plotting all those samples means, what if I plotted all those samples standard deviations? No, yes, maybe, no, not really. So one big change would be that the smallest the standard deviation can be is 0. There's no way it could be negative. So over here, I could be talking about temperatures or profit, which could be negative. I could have all kinds of negatives. Can a standard deviation be negative? No. So it's going to have to start at 0. It doesn't go off in both directions forever. Okay, maybe. And what's really, really cool, oh, geez, okay. All right, stay with me, kids. What's really kind of nifty is if I do this, right? If I do this, I take, let's say, a sample of 31 things, every possible sample of 31 things, and I plot the standard deviation, I'm going to get a picture that looks sort of like this. Does that look normal? Does anyone know what that is? Something that starts with the letters SK. That shape, how would you describe this shape, this distribution? Does anyone remember? It starts with the letters SK. Skeletor? No. Anybody? Well, no. Skew, skew, SK. Skewness, I like it. Thank you, Rudy. So this is skewed to the right. Okay. This is the shape that you would get if you did what I just said. Take every possible sample of some size and plot it. You would get this shape. Okay, maybe. And the reason that kind of makes sense, that if I take a sample, there should be very few samples that have a standard deviation of 0, right? There should be very few samples that have a standard deviation of 0. Okay, I like it. And then there should be a decent chunk that have something in here. And then there should be very few that are really huge standard deviations. All right, and to be honest, this isn't quite the picture of this. So let me see. Let me back up a little bit. So this one, let's say these are z-scores, right? So what governs this? What formula governs this? There's a few of them. There's a few formulas that govern this. There's this one. There's this one. There's this one. don't all of those follow this if they meet the right conditions? Sorry, guys. Don't all of these, if n is greater than 30, if I know it's normal, or if np nq greater than or equal to 5, if that's true, don't all of these formulas deal with this shape? Yes, we know this. We've been working with this for a while. Okay, maybe. So over here, this guy, which I affectionately call the Jabba the Hutt distribution. You don't have to if you don't like Star Wars. This guy over there, here's one of the main formulas for this guy. So I really want you to see the correlation between the two. This is the distance from the mean divided by the standard deviation, right? So I've got, in fact, let's look at this case. I've got the sample mean, I've got the actual mean, and I've got the spread, right? Now this is a very different looking formula, and that kind of makes sense because this is a formula dealing with this piece. It shouldn't have the same formula, it shouldn't have the same shape, because I'm dealing with the standard deviation, which used to be about what the shape looked like. And now I'm talking about what shape do those themselves take. So why would I expect it to be the same shape? So if I took a sample from a population, I could then do this. Now this is related to this. They're kind of very similar, right? This is kind of like what the z-score would look like for this shape. I love you guys. I have no idea what you're thinking right now, but I really just want you to realize you all pretty much just swallowed the whole idea of normal distribution. You're cool with it, and we've been using it, and certain things follow this shape if they meet certain conditions. Right? So I know that sample means follow that shape if they meet n greater than 30. I know that sample proportions follow that shape, right? If they meet NP, NQ, blah, blah, right? We know all that. Okay, so here's the shape that standard deviations themselves follow, right? And then similar to a z-score, I can calculate what's called, unfortunately, it's called chi-square. Chi-square, right? Has nothing to do with Dragon Ball. Don't get too excited. Kamehameha? No, Kamehameha. Stop. Oh, now hopefully you guys, you know me. You know how this works. You know that right now we're talking about ideas. We haven't actually looked at what a problem is going to look like for you. We're just talking about ideas, right? And one thing that's really, really crazy cool, the reason this is called chi-square, this square, by the way, is a part of the notation, is this is what I would get if I folded this on itself, squaring the results. And that's kind of weird. That's a little bit too far. It's just to really quickly give you an idea why this is called chi-square. Okay. All right, now, let's take a look at a couple things. In fact, let's do this. Now that I've sat down, this is perfect. So for example, just to use the formula, what if I had n equal to 31, sigma is 11, and I get an S of 9, right? What would chi-square be? Just take a minute, maybe if I give you something you can sink your teeth into, can you figure out what chi-square would be in this situation? All right, let me see. So what will this be? It'd be 31 minus 1 times 9 squared divided by 11 squared, right? Has anyone got that? Are you guys out there? I mean, I'm trying to give you something nice and concrete to hold on to for dear life. Somebody do that for me. Tell me what it is. Ooh, dude. Yeah, let's see. That's not quite right. I don't know what you did. You might have squared the 30 also. I don't know. No, that doesn't really answer why. Did you square the 11? I don't know what happened there, Rudy. Try again. Yeah. I get 20.0826. Yeah, sure. Right? So one thing to realize is do you see how the standard deviation is under, so the sample standard deviation is less than the population standard deviation. Do you guys see that? Okay. Stay with me now. What's the only way I can get a 0 out of this equation? And you can't have n equals 1 for this, so don't get too excited. What's the only way I can get 0 out of this? Come on, we can do this. What's the only way that a fraction can equal 0? Yes, if the top is 0. And how do you make the top 0? Either n is 1, which I just said you can't do, or s is 0. So if I get a sample, how could a sample have a standard deviation of 0? Do it. Tell me. How can a sample have a standard deviation of 0? Can somebody give me like a size 3, n equals 3 sample where the standard deviation would be 0? You could do this. You know what standard deviation means, so you know what it would mean if it was 0. So you can give me 3 numbers that would have a standard deviation of 0. You can do it. What does standard deviation mean? We said this earlier. Standard deviation is I don't know if you guys, are you guys really out there? Are you guys really out there? I know this is weird. I understand. Try to latch on to what you know. Yes, Livia, spread. We know this. The standard deviation is the spread. So what's the only way that a sample could have 0 spread? Yes, all the data is the mean. So if I have a sample like 777, 777, the mean is 7. None of them get away from the mean. The spread would be 0. I like it. Do you see how that's so unlikely, isn't it? If you go out and randomly pick 3 people, how likely is it they all have the exact same age? Very unlikely. Are you guys with me? Wouldn't that be really unlikely? If you randomly picked 3 people and they all were exactly the same age, you can't tell me you wouldn't trip out just a little bit. Like, what the shit kind of weird superpower do I have? I can't use this superpower. Okay, and that's why this shape has such a small thing right at 0. It's very, very unlikely to get 0. Okay. What if these were equal to each other? What if the S equaled the sigma? What would chi-squared be? If S equals sigma, what does this part do? If S equals sigma, what would these 2 things do? Should we try it? Maybe we should try it. All right. So what if I had n equal to 10, S equal to 5, and sigma equal to 5? What do you get when you do the formula? Yeah, you get, yeah, of course you get n minus 1. If s and sigma are the same, these two are going to cancel. Therefore, chi squared would equal the degrees of freedom. Chi squared equal n minus 1. Do you guys see that? And that actually is the tallest point on this is that, because what should happen in a really well-selected sample? The variances should equal each other, right? What do you expect to happen if you take a sample? Do you expect the sample mean to be far away from the actual mean? No, you expect them to be close. Same thing happens with the standard deviations. If you take a really well-selected sample, you expect the S to be close to sigma. So the tallest peak here is related to n minus 1. Okay, that's enough of this. Okay, all right. Just want you to get a feel for this. Okay, all right. Now, I do want to show you. So here's what this table looks like. In fact, let's keep an eye on, so this chi square would equal 9, right? This chi square would equal 9. What if n equals 10, s equals 7, and sigma equals 5? Take a second and figure out what would that chi square be? What would that, from the formula, what would that chi square be? Let's see, 12, 13, 90, 115, 17.64. Let me see, what did I do? 25, oh, 49 over 25. Oh, I forgot the square. Yeah, of course. All right, you guys get 17.64. Let's see, 9 times 49 divided by 25. Yes, 17.64. All right. So let's do this. All right. Let's keep track of those. Hopefully you got those written down. And we're going to look at the table. And I want to point out some interesting things. Okay, so let me pull up this table. Where do I have this table? There it is. Okay, here it comes. This is up on Canvas. You can go download this for yourself. Where are you? There you are. All right, everybody freak out. Everybody freak out. Here is the table. This is insane. This table is really kind of crazy. So let's let it sink in. Okay. So a couple things to notice about this table. This is a little bit evil, but just the way it's done. Do you see how this table tells you the area to the right of the critical value? So, for example, look at which row would we be looking at for the example we just did? Which row here? Because of course this is degrees of freedom. So which row would we be looking at? What's the degrees of freedom for the problem we just did? Yes, n minus 1, right? So we'd be looking at this row. Now, remember the shape is this guy. There should be very little, so like, does it make sense then 1.735 has 99.5% to the right. Now, see, that's one of the most evil things about this table is that we're so used to the z-score table telling us what's below. This one tells me what's above. It's just the way it's done, unfortunately. Right? So it makes sense that a value of 1.735 would have almost 100% above it because that's so close to 0. I like it. Notice a couple things. Hopefully you notice this is not symmetric. There's no negatives, right? So for example, if I wanted to make a confidence interval using this thing, it wouldn't be 10 and negative 10, like z-scores are 1.645 and negative 1.645. It wouldn't be. There's no negatives. It's not symmetric. All right, all right. Now look at the scores we got. What seems to be right in the middle of this? What seems to be right in the middle of this is like 9. I don't know if you guys see that. So look at this row right here. Let me zoom in a little bit. Look at the 9 row. Look at the 9. And do you see how this is 90% above and 10% above? So what's right in the middle of those two looks to be about 9. If you average those two, you'll get about 9 point something. Okay, because it's not linear. So anyway, it's really close to 9. 9 is right smack dab at the tallest peak, but this is not symmetric, so it's not going to be anyway. Let me stop for a minute. Let me just stop. For the example we just did, when we did S of 7, we got a chi-square of 17.64. So see how that's just above this? That's just above this, right? So didn't we get a 17.64? You can see in the chat, 17.64. That's just above this. Why am I looking at this one? Because it's in the 9th row. And that's the one I'm dealing with. That's the degrees of freedom. Just like on the T-score chart, you live in the row that is your degrees of freedom. Same way. So we live in this row right now for this problem. And 17 is just over this guy. So about what percentage is above 17 is roughly 5%. You know, it's a little bit, so it's going to be a little less than 5%. So if I come back to my picture, 9 is like right here. 17 is going to be over there. And this is about, I already forgot what I said. 5%. So it's a little bit less than 5% in here. That is what that chart tells you. If you look up a chi-square score, it'll tell you the area above it. Now, obviously, this thing, that's actually not what we're going to be doing with this because it's not detailed enough, right? That is nowhere near detailed enough because I can't find 17.64 on here, right? I can't find exactly that. Okay, so let's talk about what we're actually going to be doing with this. So I just need to get all that out to start to get it in your brains. Oh shit, you can't hear me? Can anybody else not hear me? Can you guys hear me? One person?
I can hear you.
Huh?
I can hear you.
You can hear me. Johanna, can you hear me? Now you can hear me. Okay, I don't know what just happened. I could do this and go, but that would be me. Okay, I won't do it. Let me see. What was I going to say? All right. So I want you to realize, these are the main things I want you to realize. Why does it make sense that I cannot use the normal curve for these kind of problems? Because one of the most fundamental things it does is it models what the S's themselves do, what the standard deviations themselves do. So why in the world would they look the same as the distribution that they control the shape of? I mean, I really hope that makes some kind of sense. And real quick, can somebody this could be pushing it a little bit. Can somebody please take the square root of this number right there? What's the square root of 2.706? Somebody out there has got a calculator. What's the square root of 2.706? Does anybody have a calculator? Nobody does. Well, in fact, go a little further, Jonna. 1.644 what? I did this earlier. Where'd it go? Whoa, what just happened? Where'd that number come from? Holy shit. Oh, I see. You're just telling me that. Okay. So it's 1.645. You guys with me? Is anybody not with me? All I said was take the square root of 2.706. Right? And you got 1.645. Now do the square root of 3.841. Do the square root of 3.841. All we're doing is taking the square root. I don't understand. So all we are doing right now is me seeing if anybody paid attention earlier. Square root, for example, of 3.841. That's all I'm doing right now. Right? That's all I'm doing right now. I haven't told you why I'm doing it. It's related to something I said earlier. Do those numbers look familiar so far? Round them so I get 1.645, 1.96. Does that look familiar to anybody? No? Okay, sure. They are z-scores. Period. I don't care where you get them. You can get them from the large part of the t-score chart, but they are z-scores, right? So, this is almost too cool. I got to share this with you, even though I know you're all about to have your brains pop. So the reason that is related to what I said earlier. The chi-square shape, this chi-square distribution, is related to folding the z-score thing on itself, kind of like squaring the values. So, and again, I still haven't, God, what's wrong with me? I still haven't shown you a nuts and bolts problem you're going to need to do. We are still talking about the idea behind what it is we're using. So please don't tune out and freak out and shit. I know this is weird. I do. But have you ever heard of this shit before? Ever? Maybe some of you. Most of you, definitely not. So just let it start to sink in a little bit. So watch. This is kind of cool. Stay with me now. This is kind of cool. What if I had a normal curve? Normal. Let's go back to, see how beautiful normal curve is now? Don't you wish you were still back making confidence intervals? No? Oh, all right. You should, probably. So if I go to 1.645, can somebody tell me, and negative 1.645, can somebody tell me what areas these are? What area is that right there? You could do it. You could do it. Just tell me what area that is right there. You have to be able to do this. Nothing new, old shit. Get your z-score chart, all good. Z-score chart, look at the negative side, right? You can do it. What area is this? Anybody? Anybody? Nobody. What's happening right now? What is going on out there? Yeah. Not 0.5, but it's 0.05. Okay, right? Old shit, right? Old shit. You've got to latch on to old shit. Not everything we do is brand new. Some of it is old stuff we know, because that's how we build. We build on old stuff we know. Now, what I'm saying, and this is too cool to let go of, I have to do this, is if I folded this on top of that, if I fold this on top, right? So now it looks like, this is going to be really weird. So if I fold that on top, it's going to look like this. So now there's 10% here, right? So 5 on top of 5 is 10%, right? And this is not going to be 1.645. It's going to be this times this. What's 1.645 times 1.645? We already know what it is. It's 3.841. If I remember correctly. Or is it 2.706? I've already forgotten. Oh, yes, 2.706, yeah. So if you do 1.645 squared, you get 2.706, correct? All right, just please stay with me. All I did was fold this on top, smack. So now there's 5 and 5, 10%, and this times this is, I've already forgotten again, 2.706. All right, all right. Now watch. Do you see how right here, 10% to the right, 10% to the right is a 2.706 chi-square score. So that is just 1.645 squared. That's why they are called chi-square. Now, the minute the degrees of freedom starts growing, this kind of becomes its own thing. It doesn't relate anymore to the single normal curve. It's grows and grows and grows. Okay, all right, so let's do this. Let's finally get into the stuff that we're gonna have to do. Okay. Sorry, that's enough of the conceptual stuff. So even if you didn't understand that, even if you just understood 20% of what I just said, that's not bad. Okay, so let me make sure you guys can use this chart real quick before I go on. Let's do another problem using this chart. So let me pull the chart back up. Actually, but after I tell you this, what if n is 11 and alpha is 0.05? What's the chi-square score that I'm dealing with? Let's say it's a one-tailed test. So let's see if you guys can do this. Let me pull this back up. Right, so n is 11 and alpha is 0.05. What chi-square score are we looking at?
Is it 15.987?
Well, let's see. So here's 0.05. And what's the degrees of freedom going to be? So it looks like you're in the right column. Degrees of freedom should be not 11. What's the degrees of freedom going to be?
10.
10. So when I go right here, 10, 18.307.
Oh, I thought I would square the alpha.
No. Okay.
That's why I went to the 15.9.
No. So again, how is this chart created by folding the normal curve? You don't have to do that shit anymore. That's how it was made, right? So now if I look at 0.05 alpha right there, I can see 0.05 alpha, and I stop at the degrees of freedom, I'll get my chi-square score, 18.307 like Damar said. All right, so if you took a sample and found a sample standard deviation and its chi-square score was 18.307, that would just barely be in the top 5% of standard deviations, right? It's the top 5% largest standard deviations, right? It'd be larger than 85% of the other standard deviations. Does that make sense? Because that's 5% above it. So there must be 95% below it. All right, so be careful. So this is the whole thing. Look, the area to the right of the critical chart. So yeah, if I'm talking about a one-tailed test, these are the upper tails. That's a little too much right now. I'm about to sneeze. I love having a cold. It's fantastic, especially right now. It's really exciting. I know I've had a cold forever, but I'm just lucky. All right. So again, we got to get a little bit deeper into stuff to really get into. I love the question you're asking, Olivia, but we got to go a little deeper into stuff. So right now, I just wanted to make sure we could read the chart. So that's why I kind of said it was a one-tailed test. Did you notice that? So alpha is 0.05. Stop at degrees of freedom. Bam. I like it. Now, so everybody kind of sees how to read this chart. So if I had said, what chi-square, now watch, let me ask it this way. What chi-square has 95% above it and n is 31? Right, so let me pull this back up here. Of course, I picked 31. So what chi-square score has 95% above it? So then I'm going to look at this one, 95%, right? Because again, the whole point of this chart is it's to the right of it. So 95% above it. And I'm going to stop at the degrees of freedom, which will be 30 in this case, right? Degrees of freedom would be 30. So I get 18.493. So right now, we don't even know really what that necessarily means. But right now, I don't care. I just want you to, can you read the chart? That's all I want right now is, can you read this chart? Okay. So this is different. The z-score chart has the area below. The chi-square chart has the area above. That's a little bit evil, but we will survive. Okay. So let's get into the kind of problem we're actually going to talk about. So let me, the kind of problem we're actually going to talk about and just to remind you, remember how, is there a single formula for Z? No, there's many. There's this one, and there's this one. And there's even more if you did chapter 10, right? You get a really big ass Z-score formula. Is everybody cool with that? Aren't there multiple Z-score formulas? And if they're normal distributions, aren't they all talking about the same shape? Aren't they all falling on the same shape graph, right? Is everybody cool with that? You have to be, because you made it this far and you've been doing those and putting them in normal curves. That's what you've been doing. So for chi-square, kind of the fundamental formula for chi-square is the one we did earlier. That's the kind of fundamental one. But we're going to use a different thing. So here's the idea. How can you really test, like rolling a die and making sure that the result makes sense? You know, seeing if there's evidence that the die doesn't follow what it's supposed to. Is everybody with me so far? So if I roll a die, let's say, all right, let's do something you should totally be able to do. Let's say I roll a die. What are the possible outcomes? And this is not a D8 Dungeons and Dragons damage die. No, this is just a normal die. All right, it's not 20-sided. What are the results? What could it be? What could the outcomes be? If you roll a die, what could the outcomes be? Well, there you go. Okay. 1, 2, 3, 4, 5, 6, right? So those are the possible outcomes. How many of each do you expect? If I roll it, let's say I roll it 60 times. How many would you expect? That's why I put an E there. How many would you expect to show up of each number? How many ones, how many twos, how many threes? You could do it. You could just do this thing. Holy shit, almost dropped everything. That would have sucked. Yes, please, dear God. Everybody see that? Of course. Because you expect it to be uniform. You expect them all. There's no reason to say, well, if it's normal die, one should show up more. No, they're all going to show up equal amounts. So 60 divided by 6, I expect them all to show up 10 times. You guys with me? All right. So let's say, now how do I do an experiment? That's what I expect. I haven't actually rolled any dice yet. What would I do to check this? I would actually take a die and roll it 60 times. So then I've got O for observed. What are my observed rolls? So let's make up some shit because I don't have a die here with me. Right? So let's say that I get, I don't know, Jeff, what you got? Let's say I get 8 1s, 7 2s, 9 3s, 6 4s, 9 5s, and then what do I got left over? 2, 5, 6, 10, 11. So that would be 21 6s. Is that right? 15, 30. Yeah, okay. You guys semi-cool? I mean, I made that shit up, but what has to happen, obviously, they all have to add up to be 60 because I'm rolling this die 60 times. So if I get 8 1s, 7 2s, 9 3s, 6 4s, 9 5s, that leaves me with 21, I believe, if I did that right. 15, 15, 30, 30, 60. Yeah. How you guys, right now you should be feeling a little bit better. You have no idea how the chi-square shit's going to come in. It's not going to be that formula because I'm not talking about standard deviations now. Right? So I know right now you're probably like, what the shit are we doing about chi-square with it? No, just focus on what we talked about, right? Is there anybody not cool with what I just happened? I know this is what I should expect to happen. And let's say this is what I observed to happen. Now just tell me your gut instinct. Should there be evidence? Just looking at this. Just looking at this. Do you think this will have evidence that the die has been tampered with? Even just looking at that, does it look like there's evidence? Yeah. Why? Because there are a shit ton more 6s, right? I mean, that's right. So we know all too well that our intuition is not always correct. All right. And I'm well aware we're almost out of time. So just hang with me for a second. We almost got this thing. So obviously, the first step of what I'm about to do is what? In fact, it's based on how you figured out that this looks like it's off. What do you think the first thing I should do is to start to calculate how, I'm just going to give it away, how different these are? Obviously, the first thing I've got to do is subtract these, right? Please say yes. Okay. Now, I want you to realize also, let me try to make it the same as, oh shit, I can't remember which way the book does this. It doesn't really matter. I think it's observed minus expected. And remember we had to square stuff when we did standard deviations a million years ago? Same reasoning here. I want to square that. So real quick, what would you get here? There's a difference of 2 squared is 4. Is everybody cool so far? What would go here? I want to see how different these are. I'm going to have to square them so there's no negatives or something, right? Yeah, so 10 minus 7 is 3 squared is 9. And then here, of course, 1 squared is 1. And here, 4 squared is 16. And here, 1 squared is 1. And here, 11 squared is 121. Now, if I added all those up, it's kind of lying a little bit because I have to do it relative to what was expected. I have to see how big of a difference is this relative to this. So is 4 a big difference relative to 10? Yeah. Is 4 a big difference relative to 10 billion? No. 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 So if you were supposed to pay me $10 and you paid me 6, I'm going to be upset. If you're supposed to pay me $10 billion and $4 and you pay me $10 billion, I might be okay with that. I'm not going to feel it. $4. Anyway, I'm going to stop now. So the last thing you do with this is you take this, and I've run out of room here, and divide it by E, just to see how relatively big the difference is. Okay. So then it'd be 4 divided by 10. So this is going to be easy. 0.4, 0.9, 0.1, 1.6, 0.1, and then 12.1. Is that cool? Just dividing each of those by 10. And then if I add those up, that is like my, you're going to love this shit. That is like my chi-square star. That's like my z star. This is from my sample, right? This is what I got from my observations. I can almost feel how much you love this. So if I add those up, I'm going to get 1.43, 15.1, I think. I don't know if anybody's going to help me. If I add those up, did I forget a 0.1? Let me see, 10, let's see, 1, 3, 15.2. There we go. Oh, so chi-square star will be 15.2. All right, I know I'm over. I know I'm over, and I don't care. Give me a minute. We'll do a whole other problem again, I swear to God, right? So what is the smallest that this could possibly come out to be? You could do this. How can you make this as small as possible? What would each of these be? Considering what I do to get them. When would the difference of these be as small as possible? If they were, you could do it, you could do it, you could do it, you could do it. If these were what? If these were what, then the difference would be as small as possible. How do you make the difference small? If you make the numbers themselves, you can do it. Somebody just say it.
Near 10?
Yes. If these are close, if these are the same. So if what I see is exactly the same as what I expected to see, that is obviously not evidence that something is different, that somebody tampered. You guys with me? Now, do I expect that to happen? No. If I roll the die 60 times, it could have different numbers. This could happen. So here's the idea. Here's what the thing looks like, right? Here's 0. So what I'm looking for is enough evidence that the sample was so far away from 0 that it's evidence that something happened. Now, I'm not going to make you do an entire hypothesis. That's all you can tell it could be, right, from what I'm saying. All right, I really want to finish this. I know I'm rushing right now because we're out of time, but and then we'll do more problems. So don't freak out. We're going to do more problems. How many categories were there here? How many things could have happened? How many categories? 6. So the degrees of freedom for this kind of problem is the categories minus 1. So it's actually called K minus 1. Why K? Because somebody who did it didn't know how to spell categories, and they said, this sounds K. All right, right? So they used the K for whatever reason. So the degrees of freedom here would be 5. So let's say I want alpha to be 0.05, and I know the degrees of freedom is 5. Can you look up the chi-square? I'll do it real quick. And again, I know I'm rushing. I know I am. So if I look up what did I say? 0.05, and I stop at 5, I get 11.071. Did we get above that? 15.2. Yeah, we got above that. We got 15.2. That is evidence that it is different, that somebody tampered with the die. That is evidence. Not like by a ton, 15.2, but it is definitely above 11.071. So it is evidence, just like we thought it should be, because that is quite out of whack. I think that's enough. I'm really sorry I had to rush at the end. I just wanted to get a whole problem in there. So next time we will do another one, at least 2 more of these things, just to fully flesh it out. You guys, all right, so hopefully just forgive me. All right, so it took a while to get the concept out there. That's enough. So if anybody has any questions, wants to hang out for a minute, there is a quiz this Wednesday, just to say that again, on chapter 12, correlation, right? So there is a quiz. Anybody need to hang out? Or you guys, you're like, all right, I'm not sure. I'm sorry, Sir Khan, but I feel like I have to be a bit of a jerk, but I'm not sure how many times I got to say that. I said that like at least 3 times just a second ago. We will do more of these. I know I rushed through this and I'm sorry. So next time we will definitely do at least 2 more of these kinds of problems. Right? I have a whole handout. I think I put it up on Canvas. A whole handout with a worked out example and another example, and then we'll do another example. Yes. So this should feel a lot like it is a hypothesis test. So if my alpha is 0.05 and my degrees of freedom are 5, because now they're based on categories for this kind of problem, I look that up and I get 11.071. That's just like my rejection region. That is my rejection region marker. Did we make it inside the rejection region with our 15.2? Yes. That's why I call this chi-square star, like Z star. This is like the Z score for the rejection region. And this is like the Z star to see where our sample fell. And sure enough, we fell further than 11.071. So we found evidence at the 0.05 level. Now, what if it would have been 0.01? Now I'm curious. If it would have been 0.01, we would have still just barely found evidence. Because then this would have been 15.086. So we would have just barely found enough evidence at a higher level of significance. So I know I have said, I will say it again. I know that was quick. I am sorry. I just really wanted to get the whole problem out there. You can watch this again, or you can wait till next time. We'll do, I've got the handout that's got the worked out example, another blank one that you guys are going to do. Okay. One is going to involve M&Ms, and the other one's going to involve cholesterol levels. Somehow those go together. So, all right. Anybody need to hang out for a bit? Or are you guys like, my God, get me out of here? I don't see a lot of people leaving. So anybody else have questions or a reason to hang out? You guys all right out there? I'm not seeing anything. I am going to shut this down because I have a 9 a.m. meeting that I have to go to. All right, there we go. All right, guys. I'm sorry that was so rushed at the end. I really am. We'll do more of that. Just don't forget the quiz on Wednesday. All right. I'll see you guys later. Bye, everybody.